Okay, we'll go ahead and get started. Can the people on Zoom hear me and see the screen okay?
Yes.
Okay, thank you. All right, so what we're going to do today is we're going to review the quiz that you had. So if anyone has any questions on that, please ask. And then we're going to start on chapter 5, which is the start of thermal chemistry, thermodynamics. So in general, the quiz was kind of a mix of grades. Some people did real well, some people had a little more difficulty with it, some were kind of in the middle. I would say of the tests and quizzes we've had so far, this was kind of more of a normal distribution of grades that you typically see. So I think in general, it was pretty good. But we'll go over it just so everyone's on the same page, because remember, next week we will have a test on chapters 3 and 4. So even though we're going to be covering 5 this week, next week the test will be on chapters 3 and 4. So the stuff on this quiz was all chapter 3, so you'll see that again. So the first 3 questions all centered around balancing equations. And I've posted these answers in Canvas. If you want to take a look at it later, you can. But what I did here is try to show you how, when I solved the problem, how I kind of walked through it. So you have the initial equation. The first thing I balanced was the carbons. And so, hold on a second. So the first thing I balanced was the carbons, which is how I got the 5 in front of the CO2. The next thing I balanced. Pardon?
Our slide didn't change.
Your slide didn't change. Well, it's
I'm
not.
staring at the PDF. It's like a quiz to answer key PDF, but not the actual slides.
So you can't see the PDF?
No.
Okay. Let me see what's going on then. Okay. Huh. Can you see it now?
Yes.
Okay, thanks for letting me know. Okay, so I'll start from the beginning again. So the first 3 were balancing equations, and what I kind of put here is a stepwise fashion of how I solved it. So the first thing I did in this equation was I balanced the carbons. And so by putting the 5 in front of the CO2, then I had 5 carbons on each side. The next thing I balanced was the hydrogens. So by putting a 5 in front of the H2O, that gives me 10 hydrogens there, and then 10 hydrogens on the left. Then it became a little bit tricky because you had to balance the oxygens out. And remember, we said that the easiest way to balance the oxygens is take advantage of that when you have just one atom, one element atom there. So we have the O2. So for me, I put 13 over 2 to balance the oxygens out. But knowing that I can't have fractional coefficients, I then went and multiplied each of them by 2. So then that gave me 2, 13, 10, and 10 for the coefficients. The second one, I started there by balancing the magnesium with the 3. Then the next thing I balanced was the nitrogen with the 2. And then finally balancing the oxygens. And so with the 6 in front of the water. Then I went and checked my hydrogens to make sure those were okay. And those balance, so I didn't need to do anything else with that. Then the third one, first thing I balanced was the aluminum. Then I went and balanced the oxygen. When I went back then and checked things, because I'm thinking, oh, I must be done. I balanced the aluminum, I balanced the oxygen. But remember, we talked about how one of the things you can do on the balancing equations is you can go and you can check and you can know pretty quickly whether you have it correct or not. So when I went back and checked that, that's where I saw that I wasn't balanced on the aluminum, because now there were 4 on the product side, on the right side. So I had to increase the aluminum up to 4 to make that balance. So then if I check that, I see with 4, 3, and 2 as the coefficients, I have my aluminum and my oxygen both balancing. So 3 examples of balancing equations. One where you had a fractional coefficient and had to go back and get rid of that fraction. One that was a little more straightforward balancing. And then finally a third one of where once you were finished balancing, you needed to go back and kind of just check to make sure everything was balanced and then make any adjustments if that was necessary. So any questions about the balancing equations? Yeah.
Can you explain on the first one how you found 13/2?
So if I go and look at after I did that third step of the balancing, so I have, if I'm looking at oxygen, I have for CO2, I have 2 times 5, and that's 10. And then I have 5 times 1 from the water, so that's 5, right? So I have 15 on the right-hand side. On the left-hand side, from that it's probably a sugar, that C5H10O2, I have 2. So I had 15 on the right-hand side, I had 2 on the left-hand side. If I subtract that, that's 13. And so I need to get 13 more oxygens on the left-hand side. What I'm using to balance is O2. So if I put 13 over 2, 2 times 13 over 2 is 13. That's how I got to the 13. Does that make any sense, or?
That makes sense.
Yeah, okay. Any other questions on the balancing equations? Okay, so you'll see this on the test. I think you all can figure that out. So the next question was just, what type of reaction is this? Is this a combustion, decomposition, or combination? The key there is whenever you see O2, that's a combustion reaction. Okay, now let's go to the math problems. So number 5, what's the weight percent of carbon in the following compound? You were given the atomic weights. So what you needed to do is you needed to take the atomic weight information and calculate 2 things. So in the numerator, since you wanted to know percent carbon, you wanted to find out how much of the weight was attributed to carbon. So there were 22 carbon atoms in this molecule. So you would take 22 times the atomic weight. And then in the denominator, you want to find essentially the molecular weight of the compound. So for that, you would take the number of carbon, 22, times the atomic weight of carbon, which is 12, plus the number of hydrogens, which was 24, times the atomic weight of hydrogen, which is 1, plus the number of nitrogen atoms, which was 2, times its atomic weight, which is 14. And then finally, plus the number of oxygens, which is 8, times its atomic weight of 16. So that added up, and the denominator is the molecular weight of the compound. And then the 100 comes in there because whenever you're saying you want a percentage, What that means is you're multiplying your answer times 100 to give it that percent. So if you did all that math correctly, you would have gotten 59.4%. Okay, number 6. If you have 10 milligrams of C6H10OS2, how many molecules do you have? And then you were given the atomic weights. So you were not given Avogadro's number because you were asked to memorize that, but you would need that also. The one thing that some people missed was when we talk about working in moles and things like that, we have to get it into grams, and it was given in milligrams. So you needed to, the first thing you needed to do was to convert 10 milligrams into grams. And that's where 10 to the minus third grams is equal to 1 milligram. Then you would need to know the molecular weight of the compound. So kind of how I described in question 5, how to do the molecular weight, you do a similar thing here. So if you had, for the carbon, 6 times 12, then plus the hydrogen, which is 10 times 1, plus the oxygen, which is 1 times 16, plus the sulfur, which is 2 times 32. You do all that math and the molecular weight's 162.29. So you use that ratio of 1 mole of this compound is this many grams to then convert that grams to moles. And then here's where Avogadro's number came into play, needing to remember that that's 6.02 times 10 to the 23rd molecules per mole. If you do that math correctly, then you would get 3.71 times 10 to the 19. The last question on the quiz, number 7, and this number 7, I'll just point out, was essentially one of the homework problems. The only difference was, I think I said it was 20 grams instead of 10 grams. So if it looked familiar, it's because you may have seen it if you did the homework. So if you produce 20 grams of N2, how many grams of NaN3 did you start with? You were given the equation and then atomic weights. And so one of the key takeaways for the equation was knowing what those mole ratios were. And so you needed to change 20 grams of N2 into whatever number of grams of NaN3 you would get. And so we had to convert things into moles and then use mole ratio to solve this problem. So the 20.0 grams of N2, you needed to calculate that molecular weight, which would be 2 times 14. So that's where the 28 comes from. So now you have moles of N2 in your numerator. So in order to cancel out that moles of N2, you would need moles of N2 in your denominator and then moles of NaN3 in your numerator. So then you have 2 moles of NaN3 divided by 3 moles of N2. Those N2 moles units cancel. Now you're in moles of NaN3. Then finally, you can use that molecular weight of NaN3, which is 65.02. So once again, you get that by taking 1 times the sodium molecular weight and 3 times the nitrogen molecular weight. And then by having 1 mole of NaN3 in the denominator and the atomic weight, or the molecular weight in the numerator, you now have it in units of grams, and you get 30.9. So, like I said, one of the key things here was correctly using the mole ratio that you got from the chemical equation. So, first part of the quiz, balancing equations. Second part, some of the math that we use associated with converting into moles or molecules, things like that, taking advantage of information on mole ratios that we get from the equations. As I said before, you'll see this stuff again next week on the exam. It'll be similar, there'll be similar stuff to this. So if there's something you're uncertain about, you can certainly ask me now or ask me later. You can go back and take a look at homework problems or something like that, but it's important that you get comfortable doing these types of calculations. Does anyone have any questions about any of the quiz problems?
It's not a question, but I felt rushed trying to do like the last 2 questions.
Uh-huh. Yeah, well, time is, because of the fact that we're giving the quiz remotely to most of the students, time for all the quizzes and tests will be a factor. So I do try and give what I think is a reasonable amount of time, but yet people have to kind of keep going and they can't sit and think about something for, 5 minutes on a question and things like that. So there is a possibility you could feel rushed if you get hung up on a problem or something like that. But that's, one of the things that the quiz does allow me to see, given this, is it tells me how much time each student spent on the quiz and average times in that. And I think overall, people are getting things done with some time to spare. So I don't doubt that there is a feel of a little bit of pressure from the time, but that's going to be, if we were in class and everyone taking in the class, time would be less of a factor. But because we're not, and they're essentially open book tests, and I think I said this in the beginning, I don't want everyone just looking up all the answers. That doesn't really tell me if people are learning or not. So that's the reason for having the time as a component on the exam. Any other questions or comments? Okay, so we're gonna start chapter 5 today. I'm not certain how far we'll get into it, but we're gonna start that today. And there's a couple things I want to say about chapter 5 and just kind of about things going forward. Chapter 5 will be some intro to thermodynamics type stuff, some thermochemistry. And so as we start doing this chapter, and really pretty much from here on, not that it wasn't important to look at the homework and try the homework before, but it's going to be even more important now. If you are one of the students who isn't a fan of math and find that a little trickier, then it's going to be even more important that you work on the homework, because there's going to be more things like these last 3 questions on the quiz going forward than there has been so far. And because of that, one of the things that I'm going to do or have done is, for chapter 5, I've went ahead and created a folder in Canvas under the files heading, and it's homework answers. And so I've posted all of the answers to the homework. And by that I mean, because before you could look in the back of the book and see the answer, but I work all the problems out. And so I went ahead and just posted my calculations and all that, so that you can take a look at it when you're working on the homework. And if you get stuck on something, or you want to just see exactly how I did the problem, you can see that. The negative to that is it's all handwritten. So hopefully you don't have too much trouble reading my handwriting. But I can't stress this enough. It's going to be really important to work on some of the homework problems and get comfortable doing some of the calculations in that. We start doing some of this stuff, and all the bits about keeping your units straight and dimensional analysis and all that is really going to become more important for you when you do the math problems. So I'm hoping that by posting the worked out problems will be helpful to you, but take a look at that and use that as a guide when you're doing the homework. Okay. The other thing that I'm going to mention is, and this is pertaining to the lab, is it's very, very important for you, whether you're going to be a chemistry major or any type of science major, that you get to where you can properly graph data, okay? And I know in looking at my 2 lab sections, it's clear that we have some work to do to get people comfortable doing that. And so I do just want to remind everyone that if you don't have access to a good copy of Excel or something like that, in the ISB down on the 2nd floor there's that computer lab. Everyone has access to there. You can go in there and use those computers to do the plots. But in this week's lab, there will be another opportunity to do scientific plotting. And to be honest with you, I think of the next 5 labs we have, 4 of the 5 are going to have a lot of plotting. And if you go forward at any type of scientific career, whether it's chemistry, biology, exercise science, whatever, you're going to do plotting, I'm telling you. So you really need to get comfortable doing this and get good at it. So you're going to get some more opportunities in lab to do that. If you are confused by it or have problems with it, please talk to your lab instructor, whether it's me or one of the other instructors. That's really, really important. Okay, so that's my little speech on lab plotting. But you know, it has nothing to do with what your grade's going to be in this class, to be honest with you. That's minor in the scheme of things. You know, a lot of the stuff we do in here, some of it you'll use later on, some of it you won't. The plotting you're going to use, I'm telling you. So anyway. All right, let me pull up the slides for chapter 5 and then we'll get started on that. Okay, can everybody on Zoom see the chapter 5 slide?
Yes.
Okay, thank you. Okay, so thermochemistry. So if you think back to chapter 1, we talked a little bit about energy. And we said that energy is the ability to do work or transfer heat. So in this chapter, we're going to start talking about thermodynamics. And thermodynamics is a whole topic in chemistry that deals with studying energy and its transformations. And for the most part, when we talk thermodynamics and we talk about thermochemistry, we're talking about heat movement, okay? Putting energy in, energy coming out. So putting heat in, heat coming out. You'll hear terms like exothermic and endothermic. And that's really a big deal in chemistry because just about every reaction that you have involves some transfer of energy, some transfer of heat. Some reactions you have to put energy or heat into to make them go, to make them react. Other ones will react, but then they'll give off heat. And you can literally feel the beaker getting warmer, for instance, when you mix the solutions. So this is a big topic in chemistry. There's a lot of calculations that go with this. We'll touch on some in this chapter. We have some more later on, but this is, in my mind, you know, so far we've had 4 chapters and we've learned some basic things in the world of chemistry. To me, chapter 5 is kind of the start of kind of really starting to learn more in-depth chemistry. So it's exciting, right? For those of you on Zoom, the people in the room are standing up and jumping around. They're so excited. So too bad you're not here to see it. It's a thing of beauty. So, okay. So when we talk about chemical energy, it's mostly potential energy. Remember we talked about potential energy and kinetic energy? And potential energy was you're in a situation where you have the potential to have energy exchanges, but you just haven't realized it yet. And so with molecules, there's something called electrostatic potential energy. And this is the equation that describes that, where E, capital E with a little EI, it stands for electrostatic potential energy. The K is a proportionality constant. And there's the value of that, 8.99 times 10 to the 9th. That's something that if you were doing a calculation with this formula, you'd be given that proportionality constant. That's not something I would expect you to memorize. The Q's are the electrical charges on the atoms or molecules, depending on what you have. And then finally, just a reminder that when we talk about energy, there's several different units that we use, but probably the most common is the joule. And that just reminds you what a joule is. It's kilogram meter squared per second squared. What I want to point out too, let's go back and take a look at that proportionality constant and the units on that. So the units on the proportionality constants are joules, meters per coulomb squared. So if we see where it fits into the formula, we see it's K times Q1 times Q2 divided by D. D is the distance between the molecules. Q is the charge of the molecules. And so that'll be coulombs. So what that tells me is, in order for my units to cancel out on that proportionality factor and be left with just joules, then I would have to have the D in meters. And then of course the Q's would have to be in coulombs. So why is that important? It's important because I guarantee you, if you do a problem with this type of equation, they're never going to give you the distance in meters. Because we're talking about atoms or molecules, right? The distance between that. You're not going to say that's 2 meters away or something. That'd be crazy. So you're going to have angstroms or nanometers or something, some really tiny amount, but you got to switch it to meters to make the formula work. So that's a key thing in doing these problems, is remembering what units do I have to be in to make the equation work. If we look at the diagram on the right, it kind of talks us through a little bit of this. And so there's a couple things we want to remember, is that if we look at Q1 on Q2 on the top part and Q1 and Q2 on the bottom part, we see that on the top part, because they're both blue, that's implying that they're the same charge. And what did we say before? Like charges repel, okay? In the bottom, we have a red one and a blue one, so that is implying that they're opposite charges. One is negative, one is positive. And we said earlier on that opposites attract. So if you have a negative charge and a positive charge, there's an attraction there. So a real important distinction there, to remember that like charges repel, opposite charges attract. On the top one, where we have the repulsion, if they're close together, there's greater repulsion, okay? It's it's no different than it would be in real life, is that if you're standing right next to someone and you don't really like them very much, there's a greater chance of being aggravated with each other because you're right there. If you're halfway across town and you don't like them that much, it's kind of out of sight, out of mind. They're not bugging me that much. You look on the bottom, it's the same thing for the attraction. The closer they are together, the greater their attraction. Once again, that's similar to how anything would be. You know, if there's someone you like and you're next to them, you're probably going to interact with them. There's a greater interaction there. If you're far away from them, less chance of interaction. And so what we see is on top, greater separation then, of course, has less repulsion. And this just translates to a lower electrostatic potential energy. The potential for problems are less when you're far apart. Potential for problem more when you're close together. On the bottom, potential for something good to happen is greater when you are close. Potential for something good to happen is less when you're far apart. So conceptually, that diagram on the right kind of tells us what the numbers that will generate on the left using that formula would mean. So as we said, when we talk about electrostatic attraction, we're talking about attraction between oppositely charged ions. And so when chemical bonds are formed, so in other words, when that attraction becomes so great that we now have a bond formed, energy is given off, okay? In order to break a bond, energy is consumed. You have to put energy into it. And think of it no different as if two people were standing there and they were holding each other's hands and you wanted them to let go, what would you have to do? You'd have to push them apart or push their hands down or do something. You'd have to put some effort into it to get them from holding hands, okay? But you think about it, if they go to hold their hands together, they want to do that, you really don't have to do much. They just go ahead and hold hands, right? So if any time you want to break a bond, you have to put energy into it. And this is why we are concerned about these different types of energy calculations that we'll talk about. And it gets a little confusing because there's different types of energy calculations that we'll go through, but fundamentally, it's all about the same thing. Is you're trying to understand, what do I need to do to form a bond? What do I need to do to break a bond? And in general, to form a bond, you don't have to put energy into it. To break a bond, you almost always have to put energy into it. And that's where you'll see in a little bit, that's where we'll define exothermic and endothermic and things like that. So the first law of thermodynamics. And remember, we said early on that if something's a law, it's that way, it's right all the time. We've got math to back it up. We've got a lot of data to back it up. So it means we really have confidence that this is what's going on. And the first law of thermodynamics simply says that energy can be converted from one form to another, but you can't create it or destroy it. So there's a certain amount of energy going on, and you can move it from one form to another, but you can't create it, you can't destroy it. It's kind of like when we talked about the atoms. We can rearrange them, but we can't destroy them, we can't create them. So some examples are, you heat your home, so you need chemical energy, and then that's converted to heat. Sunlight is converted to chemical energy in plants. There's a whole bunch of examples, but we've talked about the combustion reaction and driving the car and that. Where there's energy, there's potential energy in the gasoline. And then when you do the combustion reaction, you free that energy up, and that's what helps your car move, powers your vehicle. So in none of those cases did we create or destroy energy. We just moved it around, okay? And that's what first law of thermodynamics says. You can convert it from form to form, but you don't destroy it and you don't create it. So now is when we're going to have some terminology of way people talk about these kind of systems. And when we're studying this and we're looking at a certain heat flow problem, we call that the system. So in this case, we have a piston in this example. So that's supposed to be a piston. Hopefully everyone knows what a piston is, but in this case, it's a closed, sealed up container with some gas in it. And then the round thing with the long shaft is the piston, and that can go up and down. And so in there, you see hydrogen molecules and oxygen molecules. So in this case, the system is the hydrogen and oxygen molecules. That's what we're studying. The surroundings is everything else. So the surroundings are that cylinder, it's the piston, and anything else in the world. But for us, the system would be the hydrogen and the oxygen molecules, and the surroundings are the cylinder, the piston, and everything else around it. So there's several types of systems. One is an open system, and that is defined as something where you can exchange heat and mass with its surroundings. So what that means is if it's an open system and I do something to it, I do something to it to cause some type of reaction, then it can give off heat to the surroundings, or it can absorb heat from the surroundings. And also the stuff that's in there that I'm reacting can leave the container. Think of it that way. Okay, so that would be an open system. A closed system is similar, except you can't lose mass. So in other words, you keep the stuff from spilling out. So and this piston example is a closed system, because we can have that piston go up and down. If the gas expands or something like that, or the pressure increases, it can push that piston up, but the hydrogen and oxygen molecules can't leave the container. So we've got them enclosed. And so closed systems are, you can give off heat, so you could do something and you could feel a temperature change. So it can have an exchange of heat with the surroundings, or heat can go in if it's endothermic, but the mass doesn't change. And then finally, isolated system is when you control the heat and you control the mass. The one that's most common for study is the closed system, number 2. And that's what we'll mostly be talking about. And the reason for that is isolated system is just really hard to do. And open system, if you have mass moving and you have heat moving, it just gets more complicated and it's harder to figure stuff out. So number 2, the closed system is the one you're most likely to see. And once again, on the right there with our piston example, we're talking about a closed system. And so if you do something to that system to cause a change with the hydrogen and oxygen, a couple things can happen. One is you can give heat off, or heat can go in, or that piston can move up or the piston can go down. And if the piston is moving, what kind of energy is that? That would be work, okay? Because you're doing something like that. So it's real common in this type of study to have like this piston example, because that's an easy way to show work. If you're pushing the piston up, you're doing work. If your piston's going down, work's being done on the system, okay? So you'll see this piston thing, and you'll see this in the homework, I believe. It's just a common way to express some of this and study some of this type of chemistry. we talk about internal energy of a system, and that's the sum of the kinetic and the potential energy. So remember, kinetic energy is the actual motion going on. Potential energy is the potential to do things. And so it's also for all the components of the system, and it's usually designated by this capital E. The interesting thing about internal energy is that usually we don't know what it is. And so we look for changes in it. And that's this triangle with an E, so delta E. So whenever you see that triangle in front of it, that means that you're measuring a change. It's not an absolute number. It's we were here and now we're someplace else. What's that difference that we're getting? So in our plot here at the bottom, we have initial energy at the initial state of the system. That's the straight line going across. And then we have an example where the final state of the energy goes down, and we have an example of where it goes up. So let's look at the first one, the one going down. I think that's the one with the red arrow. So there, energy went down, so we lost energy to our surroundings. Because it went down, then delta E is going to be negative. So we started with a bigger number, now we're a smaller number, it decreased. If we put energy into the system, then that final energy will go up and we'll have a positive value for that change. So once again, we're not saying we know what that initial energy number is. We're just saying we're measuring that difference in the two. So loss of energy to surroundings. So in other words, if we did something, I could feel it getting hotter, for instance, then that would be a loss of energy. We'll learn in a second, that's called exothermic. And then putting energy into the system where the system has gained energy, that change in energy goes up, and that's a positive value, and that'll be called endothermic. Could you mute your phone, please, or your computer? So by definition, the change in internal energy is the final energy minus the initial energy. Okay, and that's how we get that negative and positive. So final energy minus initial energy is that change in energy. And there's just a little example there on the right of what that looks like. So if the delta E is positive, we've absorbed energy. That means our final energy state is bigger than what our initial is. Okay. If it's negative, then that tells us the system has released energy to the surroundings. And so you always have two choices with what's going on. Did energy go into it or did energy come out of it? Okay, if energy went into it, you're going to have a positive number. If energy came out of it, you're going to have a negative number. So really, if you don't get hung up in a lot of the stuff, and you can break it down pretty simply like that. There's only two things really energy does, either goes in or it comes out. Now, how you get to that number, that's where some of the math comes in and things like that. But fundamentally, it really comes down to those two things. And if you think about the holding hand example, if you want to get two people to stop holding hands, you got to put some energy into it. You got to break those bonds. At forming, usually that usually doesn't require putting energy into it. It So when we talk about thermodynamic quantities, there's three parts to it. There's a number, of course, and a unit. So that's no different than what we've had on pretty much everything we've talked about so far. We always have a number and we have units. But what's different about the thermodynamic stuff is you have a sign. You want to know, is it positive or negative? Because positive or negative tells us if heat's coming in or heat's going out. So the sign is critically important. You know, there's some times where if I'm looking at someone's test or a grade or something and they forget to put the positive or negative sign, it's not that big a deal. You just think, oh, they just forgot or something. In this kind of stuff, it's a big deal because whether it's positive or negative has a big implication, okay? So once again, I'm going to say it again, just because it's that important. If delta E is positive, that means the system gained energy. So energy went into it, heat went into it. If delta E is negative, then that means the system lost energy to the surroundings or gave off heat. We tend to use the words energy and heat interchangeably, which isn't totally correct, but for the most part it is. So if thinking about energy going in or out doesn't make sense to you, just think of it as heat going in or out, because in reality, that's what it usually is. Not always, but that's what it usually is. Sometimes you have the work component, but really, most of the time it's heat that we're talking about. Any questions on the heat going in being positive, heat coming out negative? Okay. So now let's talk about internal energy. So when energy is exchanged between the systems and surroundings, it's exchanged as either heat or work. And so delta E can also be expressed as Q, which is heat, plus work. And depending upon the type of system it is, work has more or less importance. If it's one of those piston examples that we had with the hydrogen and oxygen gases, then it's pretty easy to see work at play there because you can move that piston up and down. If it's not a system that has something like that, then really you tend to be talking just about heat. So for whether it's heat, work, or energy, you're going to see a common theme here. A positive for Q means it gains heat. A positive for W means work has been done on the system. A positive for E, delta E, that's a net gain of energy by the system. By the same token, if Q is negative, that means the system lost heat. If W is negative, means the system did some work. And if E is negative, then you had a net loss of energy. This sentence at the bottom really sums it all up. In general, if a system picks something up, it's positive. If it gives something off, it's negative. So if the system is giving off heat, or if it's doing work, or that energy is changing, then if it's doing something, it's negative. It's expending something. If it's not, if stuff's coming into it, if it's picking it up, if it's gaining heat, if someone's doing work on the system, things like that, then it's positive. So this sign conventions for all this stuff, like I said, the sentence at the bottom really sums it up, I think, very well. Okay, so I've used the terms endothermic and exothermic a little bit, but now we're gonna put it out there and say this is how we're going to talk about this heat flow from now on. Is that when heat is absorbed by the system from the surroundings, so in other words, when heat goes into something, that's called endothermic, and that's always positive. So if you put energy into something, you put heat into something, That's called an endothermic process, and it'll have a positive sign associated with it. So the opposite to endothermic is exothermic. And exothermic is heat's given off when something occurs. So maybe you mix two chemicals together and you feel the beaker and it feels warm. That's exothermic. That reaction gave off heat, gave off energy. And by definition, exothermic reactions, exothermic processes are negative. The example here they have is some potassium metal put in water. And if you've ever seen that happen, potassium metal and water catches on fire. That's an exothermic reaction. That's an easy one. Usually they're not that dramatic, but when you say something is an exothermic reaction, it means I mix them together, the reaction goes, I didn't have to put any energy into it, and it's going to give off some energy. So in that case, you must have had a lot of potential energy there because it was able to generate all that energy when it reacted. So just to say this again, heat absorbed by the system, endo. So into, endo, however you want to remember it. Exo, you think of like exoskeleton and stuff like that. Exo to me is going out. And so exothermic means you're releasing energy. Yeah.
So would like an endothermic reaction get colder? Or just should say?
Well, it could. Well, it would. Usually when you're talking about an so there's some reactions, you mix them together and you feel it get cool. And it's pulling the energy in from the surroundings. That happens sometimes. What's more common is you put two things together and you have to heat it up to get the reaction to go. So you don't feel it cool, but in order for the reaction to go, you have to say run it at 60 degrees C. It won't run at room temperature because it needs that energy into it to make the reaction go. That's probably the more common. But there are examples of where you just mix the stuff together and it'll be cool, and that's just a naturally endothermic.
Okay.
But kind of the reality is that most reactions require some type of energy input for them to go. You know, some you can do at room temperature, but a lot of them you got to put some energy, not a lot necessarily, you got to put some energy in to make it go. And that gets into some other energy type calculations you can do, which I think we talk about next semester, but yeah, but your example is correct. That would be endothermic. Okay, there's something called a state function. And when we work on these like energy calculations, is that we don't know the internal energy of the system necessarily. And it's really hard to figure that kind of stuff out. And so we're usually just interested in the change. And we do know that the internal energy of the system is independent of how you got there, okay? So I think of it as, when I drive home tonight, there's a bunch of different ways I can get there. And no one really cares which way I go, as long as I wind up at home. And so that would be an example of a state function, is you know where I started here at school, and then I wound up at home, but how I got there really wasn't that important. And that's what a state function is. A state function is that what you're trying to measure is independent of the path you took to get there. And so they give an example of water here, where they have water at 25 degrees C. Well, if our goal is to have water at 25 degrees C, we don't really care if we started from frozen water or steam. We just want water at 25 degrees. And so the process from going from ice to room temperature water or boiling water to room temperature water, those are different, right? So the one with if I had an ice cube and I wanted to get to 25 degrees C, would that process be endothermic or exothermic? What do I have to do to take frozen water and get it to room temperature?
Is it endothermic?
You have to heat it up, right? You have to put energy into it. You'd have to heat it up. Even if heating up is just simply setting it on the table at room temperature and watching it melt, you still are heating it up. It's pulling in energy, pulling in heat from the surroundings. If I have hot water and then I want it to get to room temperature, I have to get rid of energy. I have to pull energy out, right? So the bottom one, I have to put energy into, I have to take energy out. The top one, I have to put it in, change the energy there. So endothermic, I have to give off heat in the top one, so that would be exothermic. I have to get rid of that. So since with internal energy, it's a state function because we're not concerned about how you got there. We're just concerned about where you start and where you end. We don't care about the path of how we arrive there. So because of that, delta E only depends on initial and final. So we said that delta E is a state function, but the things that make up the energy, the heat and the work, those aren't state functions. And here's an example of that. So on the left, A, you have a battery, and then you have like a little heating coil that the battery is going to power. And then on the right, you have a fan that the battery is going to power. If you hook the battery up to those two things, all that's going to happen on the left is the battery is going to discharge and it's going to heat up that coil. So the energy transfer from that battery just is heat. That's all that's happening. You're generating heat that's lost through that coil. So it's giving off heat that way. The one with the fan, to power that fan, you're going to have some actual work done because the fan's going to be turning, right? So that's work being done. And then it's also going to be giving off a little bit of heat too. You'll feel some heat around that motor of the fan. So in that case, that discharging of the battery has a heat component and it has a work component. On the left, we just had a heat component. So the path home that each of those took were different. One was strictly heat, one was heat and work. But where you got to is the same. You started with a certain amount of energy in the battery. You discharged the battery, lost that energy. And so then, from a state function perspective, that delta E would be exactly the same in both of those examples. But because work and energies aren't state functions, there's a different path that gets you there. Okay, let's talk about work for a moment. So as I said earlier, we talk about work and we talk about heat, and there are some examples of where you worry about the work component, but really it's almost always heat changes. The biggest exception that we'll talk about are these gas type problems where you can have the cylinder, the gas type cylinder, and then move that cylinder up and down to show if it's giving off work or work being done on it. And so here they show you that work equals minus pressure times the change in volume. And so what you're seeing here is you're seeing that cylinder, that piston moving up and down. If it moves up, the system's doing work. If it moves down, work is being done on the system. So once again, if it's moving up, is that exothermic or endothermic? That's exo because it's doing work on. So that would be a negative value. If it's going down and you're doing work on the system, we said that's a positive value because we're doing something to it. We're putting something into it. This is an example of what we were talking about where they have some gases in here and they're using that little cylinder to see how the piston is moving. In this case, the piston is going up and it tells us that the work is negative because work is being done by the system. So here's some homework that I would ask you to take a look at over the stuff we just talked about. Here is a couple of the problems. I just have one problem here as an example to show you what it's going to look like. And like I said before, this is on Canvas now under Files and then Homework Answers. So I have all the chapter homeworks written out like this. So bear with my handwriting. I know it's not the greatest, but you should be able to get an idea of how to do the homework from this. So in this one, we have that initial energy formula that we had where K is the constant, Q1 and 2 are the charges, and D is the distance. And I don't remember the exact wording on the problem, but I just want to point out a couple things. So the 8.99 times 10 to the 9th, that's a constant. That's something you would be given in a homework problem or in a test problem. The charges for this are typically around this 10 to the minus 19. The negative 1.6, that's probably an electron. The positive 1.6 is probably a proton, would be my guess. And that kind of information you're usually given too. The key is just to make sure you got the right units. The one that usually is a little different is, so you see 53 times 10 to the minus 12 meters. I don't remember what that one was given in, but I guarantee you it wasn't listed as 53 times 10 to the minus 12 meters. It was 5.3 whatever, or it was, 5 nanometers or 5 picometers or whatever. And then you would have to convert that into the meter. And then you would have to do the calculation to get the correct answer. So I'll mention this again also, because I think some people are still kind of struggling with this a little bit. So please use this as a way to test your calculator skills. You're going to have a lot of calculations with exponents. So there we've got 10 to the 9th, we've got 10 to the minus 19th, 10 to the minus 19th. Then a division by 10 to the minus 12. You got to get to where you have confidence in your ability to use your calculator to generate the right answer, okay? Because one of the negatives to the way we're testing this semester is, normally you would show all your work and write things out, and then you have the potential to get some partial credit. So the bad thing about the way we're doing it this semester is we're not writing it all out, and so you either get it all right or you get it all wrong. So it's really critical that you know how to use your calculator, especially with the scientific notation, to be able to get the right answer. B is a similar problem. You see the only thing that changed in that is it's 1 times 10 to the minus 9 meters. And then there's just some questions about changes in the potential energy and the electrostatic potential energy increase down at the bottom. So this is what the homework will look like that I've posted for all the problems. I'm not going to say you have to do every problem. That's probably not necessary, but you should, like for this one, you should be able to do one of these kind of problems like this so that you can set it up correctly in terms of the right units, and then use your calculator to generate the correct number, okay? Okay, let's talk about enthalpy for a little bit. If a process takes place at constant pressure, and usually we're at atmospheric pressure, okay? And so that would be considered constant pressure because the pressure doesn't really change in the atmosphere much. The only work done is the pressure volume work. And if the only work is done is pressure volume work, we can account for the heat flow by measuring enthalpy, H. So enthalpy is the internal energy plus the product of pressure and volume. So H equals E plus PV. So P is pressure, V is volume, H is the enthalpy, E is that energy that we just were talking about. So when a system changes at constant pressure, the change in enthalpy is called delta H. So that's that triangle in front of the H, we call that delta H. And so delta H equals the change in energy plus pressure times volume. We rewrite that by delta H equals delta E plus P times delta V. P doesn't have a delta on it because we're saying we're at constant pressure. So by definition, P doesn't change. So you're going to have one value for that. So if it was atmospheric pressure, it would be one atmosphere. But the volume might change, the energy might change. And those changes added together give us our change in enthalpy. So now what we can do is, knowing some of these other relationships we have, we can further rewrite this. And we can say, well, we know delta E is equal to heat plus work, right? And we know work is equal to minus P times delta V. So those are a couple of relationships that we talked about a little earlier today. If we go and substitute into our equation delta H equals delta E plus P times delta V, we can go and substitute delta E, we can put that's equal to Q plus W, so that's what's in parentheses there. And then we see that P delta V, if we change the sign on it, that's equal to work. So we rearrange that equation based on some of these relationships we had before to say delta E is really equal, it's equal to, delta H is equal to delta E plus P times delta V, but it's also can be rewritten as delta H equals Q plus W minus W. Well, now we simplify that even more, and at constant pressure, what we see is the change in enthalpy, delta H, is really the heat gained or lost. So that's what I've been saying for the last hour, is that we talk about work, we talk about all this stuff, but enthalpy is how we do most of these measurements, and really what we're talking about is heat flow, okay? Is heat coming in? Is it endothermic? Is heat going out? Is it exothermic? So the big assumption here is the constant pressure. If the pressure is changing, then that kind of changes the rules, but for constant pressure, we can break down that delta H equation to simply delta H equals the heat flow. We're going to go back and revisit our friends endo and exothermic. So a process is a process is endothermic when delta H is positive. Endothermic, remember again, is you're putting, in this case, heat into the system. And the process is exothermic when delta H is negative. So in other words, heat would be given off. So this goes back to what someone said earlier. In the endothermic one, when that process happened, if we felt that beaker, it might feel cold to us. If it feels warm to us, then that's definitely exothermic. So delta H, just like the other properties that we talked about earlier, if heat goes in, endothermic, heat goes out, exothermic. And from a chemistry perspective, the endo-exo stuff, to break bonds, that's always endothermic. You got to put energy into to break bonds. exothermic happens sometimes when you form things, where there's excess energy and it's given off. Because remember, energy always has to balance. That was our first rule of thermodynamics, right? Energy balances is basically what it says. You don't create it, you don't destroy it. You just move it around. Okay, so we talk about something called enthalpy of reaction. So delta H is that change in enthalpy. And you'll see this real common in thermal chemistry, is you're usually measuring changes. Where did I start? Where did I end? What's that difference? That tells me a lot about the reaction. And so the enthalpy of the reaction, which is this delta H with the small Rxn subscript, is the enthalpy of the products minus reactants. So we have a product value minus the reactant value. That's our delta H. So I said delta H with the Rxn subscript. That's called the enthalpy of reaction, or sometimes it's just called the heat of reaction. Personally, I like heat of reaction because that's really what you're talking about. What's going on heat-wise? Did heat go in? Did heat go out? And if so, how much? Because remember, when we express this kind of stuff, we're interested in the magnitude. So in other words, the number. We're interested in the units. But we're also interested in, is it plus or is it minus? Because that plus minus is important to us because it tells us if heat's going in or if heat's going out. So enthalpy is an extensive property. So who remembers what an extensive property is? What does that mean? We talked about intensive and extensive properties. Anybody remember what extensive is?
Extensive is dependent on what? I can't think of what it was dependent on, but it's dependent, right? Okay. Sorry.
Yeah, it's dependent upon how much stuff you have. Remember, like we said, color is an intensive property. So it doesn't matter if you have a little or a lot. If something's blue, it's blue. But extensive is, enthalpy is an extensive property, which means it depends on how much stuff you have. So why would that be important in chemistry? Well, it's important because, look at it this way. If I'm doing a reaction and I calculate the delta H and I find out it's an exothermic reaction, that's giving off heat, right? If I do a really small amount of material and it gives off heat, say for instance, lighting a match, okay, that's an exothermic process. You strike the match, you put energy into it, and now the reaction itself is exothermic. You got a flame going, right? Well, if I have a match, am I scared of that? Does that worry me? It doesn't worry me. I'll light a match. I'm not scared of a match. But what if that match was the size of this room and you ignited it? We'd be running, right? Because that's going to really be a big exothermic. That's why enthalpy being an extensive property and understanding that enthalpy with reactions, it does matter how much stuff you have, okay? So when we're doing these energy calculations, we're going to eventually tie it into using the number of moles we have or the number of grams we started with or things like that. Because knowing that a reaction is exothermic or endothermic is important. And then having that value, that delta H value is important. But because it's an extensive property, depending upon what we're doing, we may or may not have a problem, okay? Think of it this way, is, you know, today it was pretty cold when I drove in here, so I had to turn my car heater on. Well, it doesn't take very long for that car to heat up. My house was freezing when I got up this morning. I didn't even bother turning the heat on because by the time it would have gotten heated up, I would have been gone. It's the same process, right? But one, because it's an extensive process, you had a lot more that you had to put into it. Number two just says, for reactions, if you think about it, a lot of the reactions we have had the double arrow, right? Goes both ways. And it's just saying that if it's endothermic going one way, it's exothermic going the reverse way, and vice versa. That's all that's saying. And then finally, the last one, the enthalpy change depends on the states of the reactants and the products. And by the state, it means, is it solid, is it liquid, is it gas? You know, and use water as the example. If water was involved in the reaction, things are going to be different if water is liquid or gas or solid. So that's what they mean when they talk about the states of that. Okay, well, I think we'll stop here. This is a good stopping point. We're pretty much done. We'll pick up on Wednesday with calorimetry. This is actually a lab that you'll do next semester. We're not doing it this semester, but next semester you'll do this. So you get a little bit of practical experience with this next semester. So Wednesday, we'll pick up on chapter 5. Please start working on some of those homework problems. Like I said, I have posted my writings on the problems where I worked them out. They're on the in Canvas under files, and please take a look at that. All right, thank you.